All right. Whoa. Good morning, guys. All right, so as people start filtering in, I'm going to switch over to the doc cam. This is MAC2312, section 2. And today is the 30th of September. Today we're doing one thing. We're preparing for the exam, which means we can solve whatever problems you guys want to solve. We can do whatever it is you guys would like to do. So please pop open your homework, pop open your notes, pop open the study guide, scroll around, and let me know what problems you guys would like to see solved or what concepts you would like to see discussed. You know, type like homework 3, problem 5, or homework 10, well, we don't have homework 10, homework 5, problem 3, that sort of stuff, right into the chat there. And as soon as I've got a little list going, I will start chipping away at it. Let's see, this one I think is homework 5, right? Yeah, okay. So we want to see numbers 9 and 17 from homework 5. That sounds like a great start. And please continue doing this, right? Just keep dumping problems in the chat there. And I will do my best to get to all of them. The first one that's listed there is number 9 from homework 5. That's the integral from 0 to pi over 2 of cos t divided by the square root of 1 plus sine squared t. I'll do number 17 after this, just so we're kind of developing these things in order because the problems do get harder as we go. So there's a few ways you can do this, this guy. You can jump straight into the trig sub, or you can make a little u substitution and then do the trig sub. I think what's most natural at our level is to do the u sub first. This integral is undeniably begging for a u substitution, or I'll call it a z substitution. And the sub is for sine. Because I've got a cos t dt floating around, that's exactly what I need to substitute for sine. Sorry, I've got my phone in here. So dz will be cos t dt. That's all well and good. I'll also need to change my bounds. And this problem is a good example of why you really do need to change your bounds. Because if we didn't, if we tried to do this as an indefinite integral, I'd have to chase back through 2 substitutions before evaluating, which would be a nightmare. So instead, I say, all right, when t is 0, z is the sine of t, so z would be the sine of 0, which is 0. So my lower bound stays 0. And when t is pi over 2, z is the sine of pi over 2, which is 1. So then under this substitution, that integral becomes the integral from 0 to 1 cos t dt, that's just dz, so this will be 1 over the square root of 1 plus z squared dz. And then we look at this for just a second before realizing that this is definitely a tangent substitution. So here we're going to do another sub, this time a trigonometric substitution, z equals tan theta, where dz then is secant squared theta d theta. And again, we're going to change the bounds. When z is equal to 0, you have 0 equals tan theta. So theta would be the inverse tangent of 0, and the inverse tangent of 0 is 0. So again, my lower bound stays 0. When z is equal to 1, I have here 1 equals tan theta. So theta would be the inverse tangent of 1. The inverse tangent of 1 is pi over 4. So my new integral will run from 0 to pi over 4. My integrand here, dz, is secant squared theta. So I'll have secant squared theta upstairs. Downstairs, I'll have the square root of 1 plus tangent squared theta. And then my d theta. So the secant squared theta d theta, that comes from dz. And downstairs, 1 plus z squared is 1 plus tan squared, because z is tangent. This is the same as the integral from 0 to pi over 4 of secant squared theta over the square root of 1 plus tan squared is also secant squared theta. And of course, the square root of secant squared is secant. So this is integral 0 to pi over 4 secant squared theta over secant theta d theta. And you can cancel one of the secants. So what's left is just integral 0 to pi over 4 of secant theta d theta. And remember, the way to attack the secant integral, most people just do it by memory. It's not a problem that you want to have to solve fresh every time. We multiply by secant plus tangent over secant plus tangent, and then substitute for the denominator. And the output there is the natural log of the absolute value of secant theta plus tangent theta. So this is one that most people just know. And you evaluate between our bounds of 0 and pi over 4. Imagine for a minute that we didn't change these bounds. Then you would still get natural log of secant plus tangent, but then you'd have to draw a triangle. You'd use that triangle to go from your theta stuff back to your z stuff. Then you'd have to plug in sine t everywhere for z, and only then could you evaluate between the original bounds. That's a mess. Nobody wants to do that. Much, much easier to evaluate from here with our new bounds. So you'll have the natural log of the absolute value of the secant of pi over 4. I'll write it out. Plus the tangent of pi over 4 minus the natural log of the secant of 0 plus the tangent of 0. What is the secant of pi over 4?
Root 2 over 2.
The cosine of pi over 4 is root 2 over 2. Yeah, this is 2 over the square root of 2, which is just the square root of 2. Right? 2 to the 1 over 2 to the 1/2 is 2 to the 1 minus 1/2. It's just root 2. In other words, root 2 over 2, that number that's so infamous from your trig classes, is really just 1 over the square root of 2 with a rational denominator. So his reciprocal is just root 2 itself. Somebody else, what's the tangent of pi over 4? 1, good, Jojo. The secant of 0? Anybody? Good, that's 1. And the tangent of 0? Good. So this is the natural log root 2 plus 1 is positive, so I can lose the absolute values, minus the natural log of 1. And the natural log of 1, everybody say it with me. 0, good. All right, so this apparatus is just the natural log of root 2 plus 1. Okay, so that is a minimal, nice, concise, beautiful solution to that problem. This problem is about the right level for a test. Okay, something this difficulty would be fair game. Any questions anywhere on this problem? Okay. So the next one that was requested was number 9 from homework 5. Or this was 9, right? So 17, sorry. Yeah, going in order. 17's a little busier. I thought we did this one. Pretty sure we did this one even just last class. But we can run back through the principles here quickly. X squared minus x plus 4 over x cubed plus 2x. Is it 4? And is this indefinite? It is. All right. So this is definitely a partial fractions problem. The numerator is a polynomial of degree 2. The denominator is a polynomial of degree 3. So this is a proper rational function we're looking at. So we don't need to do any long division. We can jump straight in with the partial fraction setup. I should write my dx here, sorry. We let our reader know what we're doing. We're going to be running some partial fraction decomposition. That denominator can be factored as x times x squared plus 2. And this piece is irreducible. He's irreducible because he doesn't have any real roots. He doesn't factor, right? So you could try to factor that and discover that it doesn't factor, or you could compute the discriminant. Remember that b squared minus 4ac piece of the quadratic formula, discover that that is negative. Or you could compute the roots using the quadratic formula and discover that the roots are plus and minus I times the square root of 2. They're not real numbers. Any one of those things would tell you that this piece is irreducible. And that clues you into the PFD setup. So the x factor here contributes an a over x term in the PFD setup, and the x squared plus 2 factor there contributes a bx plus c over x squared plus 2 term in the PFD setup. So this is the correct setup for the partial fractions. My next step is to clear out the denominators. I multiply everything by x times x squared plus 2. The left-hand side is x squared minus x plus 4. The right-hand side, when I multiply this by x times x squared plus 2, the x's will cancel, so I'll just get a times x squared plus 2. Plus here I'll have parentheses bx plus c times x. We could go ahead and multiply everything out, collect terms, set coefficients equal on either side. But before I do that, I want to use the Heaviside trick to get out as much information kind of for free as I can. If I evaluate this equation or this expression star when x is 0, then I get 0 squared minus 0 plus 4 equals a times 0 squared plus 2 plus b times 0 plus c times 0. In other words, 4 equals 2a. So here a is going to be 4 over 2, which is 2. So Heaviside gets me a. But there is no number x I can plug in to make this 0, because x squared plus 2 is irreducible, has no real roots, which means b and c can't be caught with the Heaviside trick. So now we update the equation star. With the information that a is 2. So that's all the Heaviside stuff. The updated version of star says x squared minus x plus 4 is equal to 2 times x squared plus 2 plus, and I'm going to distribute the x now. I'll get bx squared plus cx. Here we go. I'll also distribute the 2, and then I'm going to combine all my like terms on the right-hand side. So this is the same as saying 2x squared plus 4 plus bx squared plus cx. In other words, I get x squared minus x plus 4 equals 2 plus b times x squared plus c times x plus 4. Okay. So now I equate coefficients. On the left over here, I've got 1 times x squared. On the right over here, I've got 2 plus b times x squared. So 1 has to equal 2 plus b. On the left here, I've got minus 1x. On the right over here, I've got c times x. So minus 1 has to be equal to c. And then it's silly to write down, but we can. The constant terms have to be equal, so we get 4 equals 4. Thank goodness. I get worried when 4 is not equal to 4. The glory of having done the Heaviside trick before doing this is that the linear system which pops out is immeasurably simpler. You don't need any row reduction or fancy matrix methods here. You just solve the first equation for b, subtract 2 from both sides, you get b equals -1, and c here is already solved. C is also -1. So now you have a, b, and c. I can take this info back here. A is 2. B and C are both -1. Which means that my integral and I shouldn't leave off my dx. My integral is equal to the integral of these things. So that's the integral of 2 over x plus the integral of -1 times x plus -1 all over x squared plus 2. Parentheses here needs to be closed. Okay. The integral on the right is not at all difficult. I can split this up as 2 times the integral of 1 over x dx. And then this guy I'm going to split up as well. This is negative x over x squared plus 2. So this will be minus integral x over x squared plus 2 dx minus integral 1 over x squared plus 2 dx. And if you have done the thing that I said you should do at the end of our last class, namely prove that arctan formula, you don't need to do any work here. This is trivial. This requires a little substitution. The first piece is 2 times the natural log of the absolute value of x. The middle piece under this substitution becomes minus 1/2 integral 1 over z dz, because the x dx is eaten up by dz. X dx is 1/2 dz, so that's where the 1/2 is coming from. And this piece, I asked you last time to prove the formula integral 1 over x squared plus a squared dx is 1 over a times the inverse tangent of x over a plus c. This is a great time saver because, yeah, you would make a tangent substitution, but why? It always comes out the same. These integrals are so common. A here is the square root of 2. Because this is 1 over x squared plus a squared. 2 is the square of root 2. So a is the square root of 2. So if you like, here I'll put the formula. This is integral 1 over x squared plus a squared dx equals 1 over a times the inverse tangent of x over a plus c. We could slap on our plus c now, but we don't have to because we still have an integral here. So I get 2 ln absolute x minus 1/2. This is the ln of absolute z minus 1 over the square root of 2 times the inverse tangent of x over the square root of 2. And now I should write my plus c because there are no more integral symbols. And then finally, z is x squared plus 2. So this is 2 ln absolute x minus 1/2 ln absolute x squared plus 2 minus 1 over root 2 times the inverse tangent of x over root 2 plus a constant. So the PFD here is not as straightforward as it can be because we do have an irreducible quadratic factor, but it's also not anything bad. If you want to see the tangent substitution for the third integral done out in its gory details, go rewatch the video from Monday, because I did do that all the way out on Monday. And that was when I told you should probably prove this formula because it will save you lots of time. To maximize our use of the review day, I'm just going to jump now to 19 from homework 5. Oh, shit, my keyboard's batteries are dying, so thank God. Okay. Ah, this is a good one. If you remember our first day talking about partial fractions, I actually gave you an example like this, and I said this is not a rational function. So first you need to make a substitution. Let's write this down. Homework 5, 19. Integral of 4e to the 2x over e to the 2x plus 12e to the x plus 32 dx. Okay. Remember that a to the b times c is the same as a to the b all to the c, which is the same as a to the c all to the b. So those e to the 2x's are really e to the x all squareds. So I'll leave the 4 in. This is e to the x all squared divided by e to the x all squared plus 12 times e to the x plus 32 dx. And hopefully writing it this way makes it easy to see the substitution we should use. This integrand is riddled with e to the x's. So I make the substitution z equals e to the x. dz is e to the x dx. So one of these e to the x's can be grouped with the dx to take care of my dz. And what's left is 4e to the x, that's 4z over z squared plus 12z plus 32 dz. So this e to the x squared is e to the x times e to the x. One of those e to the x's gets partnered with dx and becomes dz. The other e to the x from the numerator stays there, and he becomes z. The denominator is what it looks like it should be. Any questions on how to get to here? Okay, then what should I do next? Anyone?
PFD.
I heard something there, it was just very quiet.
PFD.
PFD is coming. What do I need to do in order to do the PFD? What's our first step always in PFD?
Factor the denominator.
Yeah, we gotta factor this thing. So that's z plus 8 times z plus 4. because 4 plus 8 is 12, and 4 times 8 is 32. So we're in luck. No repeated factors, no irreducible quadratics. The PFD is going to be easy. So now I step outside the integral, and I set up my partial fractions. 4z over z plus 8 times z plus 4 as a over z plus 8 plus b over z plus 4. No, Solomon, because one of those e to the x's is taken by my differential. So when I make the substitution, it's a good question. That's why I wanted to pause back there for a second. When I make the substitution z equals e to the x, I need to deal with the differential dz equals e to the x dx. This e to the x squared is the same as e to the x times e to the x. One of those gets gobbled up by dz. Okay, cool. Yeah, I think if there was a mistake, if I put this on a test, I think that would be the most likely error. Is everybody comfortable with why we landed here rather than having a z squared? Why the numerator is just z? So especially when a substitution is kind of a single step along the road on a longer problem, it's very easy to forget that differential term. Make sure you never forget the differentials when you're substituting regular sub or trig sub. The dz here is e to the x dx. That takes one of these, groups it with this. So there's only one e to the x left upstairs to call z. So if we're comfy getting to here, then that denominator factors like this, then our PFD will be this. So my next step would be to clear the denominators. When I clear the denominators, I'll get this. This is the expression that we've been calling star. And I'll get everything from Heaviside. Because I don't have any repeated factors or irreducible quadratics, I can evaluate star at z equals -4. Oh, sorry, z, not x. Z equals -4. Star becomes 4 times -4 is -16 equals a times 0 plus b times -4 plus 8 is 4. So I get -16 equals 4 times b, which means b has to be -4. If I evaluate star at z equals -8, then this piece will be 0. Over here, I'd have 4 times -8 is -32. And over here, I'll have a times -8 plus 4 is -4. In other words, -32 equals -4a. So a will be positive 32 over 4, that's 8. So I've got A and B. And that's all the PFD work. So now my integral 4z over z plus 8 times z plus 4 dz I know to be integral of 8 over z plus 8 minus 4 over z plus 4. Each of which is a simple u sub. We can split apart and pop out our constants. We get 8 integral 1 over z plus 8 dz minus 4 integral 1 over z plus 4 dz. In the first guy, I'll make the substitution u equals z plus 8. It's a simple substitution. Du is just dz. And in the second guy, I'll make the substitution w equals z plus 4. And again, simple substitution. dw is dz. So my integral will become 8 times the integral of 1 over u du minus 4 integral 1 over w dw. So that's 8 times the natural log of u minus 4 times the natural log of w plus c. Which is 8 times the natural log of z plus 8 minus 4 times the natural log of z plus 4 plus a constant. And then finally, z was e to the x. So this is 8 natural log absolute value e to the x plus 8 minus 4 natural log absolute value e to the x plus 4 plus a constant. And I can't do anything with those natural logs and exponentials because of the addition that's going on inside there, the plus 8 and the plus 4. If not for those, I could clean things up further. But as it is, this is as far as we can simplify. You could bring the 8 inside as a power and the 4 inside as a power, then combine the 2 logs into a single log if you wanted to, but for my money, it's just not worth it. Okay, questions on this fella? This is a good problem. Yeah, nothing. Oh, wow. All right. We certainly have time for more, guys. So what else would you like to see? Those are all the problems that have been requested so far, I believe. What else would you guys like to see on today, our last bit of review before the test? So again, the study guide, I don't want to solve the exact problem that's there because I don't want to see you guys just writing down my answers on your study guide. I want to see what you do. But we can take a look at this and solve something similar. I see here we do have a floating arbitrary constant. That can be a little intimidating. So maybe I will do this one. Please, though, don't just copy down my work for your study guide solution. And 10 also. 5. Yeah, that's good, okay. 10. Yeah, I like 10 a lot. Okay, we'll do 8 first. That's the integral from 0 to a of some constant times x squared times the square root of, yeah, a squared minus x squared. So here a is understood to be a positive constant, just a number. Arbitrary number, we don't have control over it, but it's not moving around. It's not depending on x at all. It is a fixed positive constant. So who can help me out? What should I try? What sort of substitution do I need to make in order to solve this integral?
Trigonometric.
Yeah, this is going to be a trig sub. If this was just a regular x instead of x squared, if this 2 wasn't here, we wouldn't need trig sub, would we? We could do it with a u sub. You could u sub for the thing under the square root, and then your differential would be negative 2x dx. This x gets sucked in, and you could proceed with the power rule. But because this is an x squared, u sub won't get me anywhere. So this radicand suggests that I should substitute using the sine function. I should do a trigonometric substitution using the sine function. So the move here is x equals a sine theta, right? Because I want a squared minus x squared to look like a squared times quantity 1 minus sine squared theta. So I'm just following my trig sub Bible. That means dx is going to be a cos theta d theta. And I need to also change my bounds. When x is equal to 0, I'll have 0 equals a sine theta, which means sine theta is 0 over a. So theta would be the inverse sine of 0, which is 0. When x is equal to a, I'll have a equals a sine theta. So 1 is equal to sine theta, which means theta is the inverse sine of 1. What is the inverse sine of 1? What is theta when x is equal to a?
Pi over 2.
Good, pi over 2. So this is my trig sub. My new integral will run from 0 to pi over 2. X squared is a squared sine squared theta. My square root is a squared minus a squared sine squared theta. And dx, don't forget, is a cos theta d theta. This is going to be a little bit unpleasant. Unpleasant because I anticipate here getting only even powers of sine and cosine. This is a squared sine squared theta times the square root of a squared times 1 minus sine squared theta. I factor in a within my square root. And then I have a cos theta d theta here chilling. I need to close that paren. There we go. So now, 1 minus sine squared is cos squared. This is integral 0 to pi over 2 a squared sine squared theta times the square root of a squared cos squared theta times a cos theta d theta, which is integral 0 to pi over 2 a squared sine squared times this is a cos theta after taking the square root, and this is a cos theta. So we get a to the 4 sine squared cos squared, like so. And there's no way of making this not unpleasant. Remember that the nasty case for sine cosine integrals is the case where all the powers are even, and that is the situation we're in now. So we need to invoke the half angle identities. Sine squared theta equals 1/2 1 minus cosine 2 theta, and cos squared theta equals 1/2 1 plus cos 2 theta. And we will need the modified version of one of those down the line here. So I'm going to leave a little bit of space for more identity work. I can pop out my a to the 4, and I'll also have a 1/4 coming from the 1/2 here, from this guy, and a 1/2 here from this guy. So that's the 4 downstairs coming from that. Then I'll have integral 0 to pi over 2. Sine squared is 1/2 times 1 minus cos 2 theta. That 1/2 contributed one of the 2's in the 1/4 there. And cos squared is 1/2 times 1 plus cos 2 theta. So this is what my next step should look like. And now I need to FOIL everything out. I need to multiply all this stuff out. You can think of this as looking like a difference of squares, right? It's like 1 minus x times 1 plus x. So it's going to be 1 minus x squared. In other words, this is going to look like a to the 4 over 4 integral 0 to pi over 2 1 minus cos squared 2 theta. The cross terms there will cancel. You'll get a plus cos 2 theta from your outers and a minus cos 2 theta from your inners. Those eat each other up. But I now need to deal with this. And the way we do that is with the modified half angle identity. Cos squared 2 theta is 1/2 1 plus cos 4 theta. I just replace theta in this line by 2 theta. If you swap theta for 2 theta, then the theta on the left becomes a 2 theta, and the 2 theta on the right becomes a 4 theta. Does everybody see how this modified half angle is a consequence of the regular one? The idea here is these are called half angle identities because the angle on the left is half of the angle on the right. It doesn't matter what the angle is, as long as this thing is half of this thing. So if I want a 2 theta here, this needs to be a 4 theta, and that's how we proceed. So I'll get a to the 4 over 4, integral 0 to pi over 2, 1 minus 1/2, 1 plus cosine of 4 theta d theta, like this. And you need to be very careful with your parentheses. I'll distribute this 1/2 and this minus sign to the 1 and to the cosine. I can't pop them out because this doesn't have a 1/2. I can't combine these directly because order of operations. But when I distribute, I'll have a to the 4 over 4, integral 0 to pi over 2, 1 minus 1/2 minus 1/2 cosine 4 theta d theta. So this is a to the 4 over 4, integral 0 to pi over 2. 1 minus 1/2 is 1/2 minus 1/2 cosine 4 theta. And now I'm ready to take an antiderivative. The 1/2 will integrate to theta over 2, or 1/2 theta. The minus 1/2 cos 4 theta will integrate to minus sine 4 theta over 8. The factor of 4 down here coming from the micro u sub, and the other 2 coming from the 1/2. And this needs to be evaluated from 0 to pi over 2. So finally, I plug in both of these bounds. When I plug in 0, everything is 0, so I only have to concern myself with the top. When I plug in pi over 2, this piece will be pi over 4. This piece will be 0 because the sine of 4 times pi over 2 is the sine of 2 pi, which is 0. So we get a to the 4 pi over 16. It's a bit of a tricky problem. There's no small amount of work to do here, but it's not unmanageable either. Questions on any of these steps? So again, I want to encourage you to go through this on your own. If you get stuck, you can refer back to this work. A wasn't 1, so the bounds work. Let's take a look at this. I think folks do have trouble with this bounds work. So changing bounds. When x is equal to 0, we get 0 equals a sine theta. So 0 over a is sine theta, which means that theta is the inverse sine of 0 over a. But 0 over a is 0. That's the inverse sine of 0, which is 0. Similarly, when x is equal to a, we have a equals a sine theta. So a over a is sine theta. In other words, theta is the inverse sine of a over a. That's the inverse sine of 1. And the inverse sine of 1 is pi over 2. So it's not that I'm plugging in 1 for a. We can't do that. That is not kosher. It's just that as I solve for the new bounds, this is the equation I'm solving. And the a's cancel. A over a is 1. So the inverse sine of 1, that's pi over 2. Yeah, good question. Make sure you take your time changing these bounds. If you're not comfortable kind of doing it in your head, like I did here, write this shit out. It's never a bad idea. Other questions or comments on this problem?
Could I see the last part of the problem?
Sure. Here were those last few steps.
Okay, thank you.
All right. This keyboard. So we wanted also to see numbers 5, let's see, 5, 10, and 8 were requested. Let me see which ones we haven't done. That was 8. 5 is this integral. And 10 is this integral. They're both fun. I think we'll have time for one of them only. Number 5 is a straightforward application of integration by parts. So I would let u be 17x and dv be e to the negative 2x dx. Run IBP once, and this will fall. The graph of e to the negative 2x is a decaying exponential. And then this x term here more or less picks the sign. So the graph of x times e to the negative 2x is going to look something like this guy, little f here. This has little f flipped over horizontally, so it can't be that. This has little f flipped over vertically, so it can't be either of these. But for the graphing portion there, I recommend that you go back to your Calc 1 notes and see if you remember how to graph x e to the negative 2x. Take the first and second derivative, figure out where your positive, negative, increasing, decreasing, concave up, concave down. It's a good practice in material that you hopefully remember. Number 10, this is an interesting problem that can be solved quickly with the right amount of insight. I don't want to rob you of the whole problem. When you solve it, you're going to need to treat it as a definite integral and handle everything properly, meaning changing your bounds, evaluating between the new bounds, all that good stuff. But the trick to this guy is to read him as e to the inverse tangent of y times 1 over 1 plus y squared dy. Does anybody see the move?
Can't you make tan to the negative first y your u, and then your du would be 1 over 1 plus y squared?
Very good. You could do this with trig sub. The bottom kind of hints at a trig sub, but the faster path is a u sub. Or a z sub. If you let z be the inverse tangent of y, then dz is 1 over 1 plus y squared dy. So this would become integral e to the z dz. Very fast problem if you know what you're doing. So again, it's a study guide problem. I want you guys to solve it on your own. I'm not going to do the definite integral, but this is how you do the indefinite integral, and the definite integral is very, very similar. You could also do this with a trigonometric substitution, y equals tan theta, which you may notice is equivalent to this one, just by taking tangent on both sides. The mechanics will look slightly different, but the process will resolve exactly the same. I think that leaves us time to attack number 5, which is this. And like I said, this is straightforward integration by parts. But you need to do a little micro u sub to pass from dv to v. So du here is just dx, but v, you have to remember how to integrate e to the negative 2x. So you integrate an exponential, you'll always get that exponential back. But then here you need to divide by negative 2. So it's a micro u sub. Now we would do the little substitution z equals negative 2x. That will give you dz equals negative 2 dx. Divide both sides by negative 2, and you'll get the integral of, or negative 1/2 times the integral of e to the z dz. So this is the way we get going on number 5. Then I follow my IBP formula. And another little micro u sub will save the day. The move here is the same as the move that we needed here, so it's not really worth writing out. Looks like this. And then to select your graph, it might be worthwhile to remember what this guide looks like. X e to the negative x. This is pretty infamous in Calc 1 classes, because it's a good minimum maximum problem. You know that the e to the negative x piece is going to want to drag everything to 0. So you're going to have this horizontal asymptote over there, and he also wants to blow up as you go off to the left. Oh, but This piece will be negative to the left of the x-axis. So you're actually going to look like this. So here's what x e to the negative x looks like. And you can try to infer from that what x e to the negative 2x would look like. And again, if you don't remember, you should go through that process of calculating y primed, factoring, setting equal to 0, so the max that you find over here is at 1. And you can build a number line for y prime to see where it should be increasing and decreasing. So it's negative over here, and sorry, positive over there, and negative over here. So I should be increasing, increasing, increasing until I get to 1. Then I turn around and I decrease, decrease, decrease. If you're having a hard time with the graphing, revisit your Calc 1 notes. Make sure that you can draw graphs well. There are several other problems in there that require you to do some graphing that may be a little bit intimidating if you think about them as test questions. Sure, here, as you go through this, I can't stop you from leaning on your graphing utilities like Wolfram Alpha and whatnot, but make sure you can graph things like this. Make sure you can graph the things that I require you to graph in the study guide. And that would be a reasonable way to make sure you're in good shape. The other hint I want to give here while we're talking about graphing is that at the beginning of the semester, when we talked about volume problems, I mentioned that there's a volume problem, some permutation of which pretty much always shows up on my exam 1. And that's a volume problem involving the natural log function or an exponential function. So you need to make sure you remember how to graph both of those. Wink, hint, nudge, nudge, nudge. We got about 5 more minutes. Any last minute stuff you guys would like to look at?
So on the exam, when we have true and false, is it going to be more like identity or theorem based, basically?
Yes.
Okay.
Yeah. You know, this is equal to that, or stuff like integral of f times integral of g equals integral of f times g. This is something I've put on as a true false, or I don't want to give them all away. This is something I've put on as a true false. Variations on these, stuff like that. Remember your symmetry arguments, right? Like even functions integrated from negative a to a can be simplified as the integral from 0 to a doubled. Odd functions integrated from negative a to a always yield 0. So make sure you remember your symmetry arguments. Make sure you remember the kind of fundamental results on integrals. How many problems? Between 10 and 20, usually somewhere around 12, 13 problems, something like that. The true false are worth less than the multiple choice. The multiple choice are worth less than the free response. The exact value that goes to each problem depends on how I have to scale things, but usually true false are worth like 2, multiple choice are worth like 3, free response are worth like 5. I might end up doubling all of those, so the scale would stay the same just to get the total to 100, but that's the relative value, so it's worthwhile to keep that in mind.
Why would you double the scale? I'm sorry, I didn't quite hear that.
Oh, because Canvas doesn't let me arbitrarily assign point values to assignments. So when I design a test in Canvas, the point value will be the direct sum of the point values of each problem. Since the exam needs to be worth 100 points in total, if the questions I write come out to be worth 50 points according to the 2-3-5 scale, then I'll double them to 4, 6, 10.
Okay.
But percentage-wise, it's exactly the same.
And so partial credit works for the free response.
Yes.
And does it work for, actually it wouldn't work for the multiple choice because we'd be
Correct.
picking an answer.
So I've taught at like 3 different institutions over the last 10 or 15 years. And I think combined from all of those places, I've awarded partial credit to a true, false, or multiple choice question, I think twice. And those were instances where students like showed all of their work and then like selected the wrong answer. So I could see that on the test, they did the work and then just like frazzled out and circled the wrong thing. But it's exceptionally rare. So usually the true, false, and multiple choice, they're either right or wrong. And then the free response questions, I try to give as much partial credit as I can. So you should show me everything you know, show every little bit of your work. And I will do my best to find as many points to give you as I possibly can. Any other questions, guys? Both of those are false. The latter is true only if f is equal to x plus a constant. No, like 1 over x squared plus 1, that's arctan, right? Not the natural log of x squared plus 1. 1 over sine of x, that's the integral of cosecant. That's negative cosecant x cotangent x. Both of those statements there are false. All right, then this is where I'm going to end it. I do have my normal office hour this afternoon from 3:30 to 4:30. If you want to meet up with me besides that time between now and the test, I have my regular office hour on Thursday. And if none of that works for you, or if you want more time, then you can email me or Canvas message me to schedule an additional office hour. Just include, if you do that, just let me know in your original email what times you would like to meet. Give me like 3 or 4 to pick from so I can try to let it conform to my schedule. And that is it. Otherwise, I will see you guys after the test next Wednesday. Okay, so because there is no class this Friday and your exam is next Monday we will not have a regular class. You're just going to go in and take the test on Canvas. The next time we will see each other in class is Wednesday. So if you'd like to meet before the test, either come to one of the 2 office hours that exist before then, or schedule an office hour with me outside of those times. If you want to schedule an office hour with me, it's very easy. Just send me a message. But I would appreciate it if in that original message, you tell me what time you want to meet. And ideally, you'd give me like 3 or 4 times to pick from, because like you, I am a little bit busy these days. All right, I'm gonna go ahead and sign out here. I hope you guys have a good rest of your day. Work hard. On Monday, make sure you come in with a clear head, nice amount of sleep, well rested, ready to rock and roll. So work real hard between now and Sunday evening, get a good bit of rest Sunday night, and then destroy that test on Monday morning. You guys are gonna do great. Take care.